What if the next generation of batteries didn't need the same chemicals we've been fighting over for years? What if one of the key ingredients could simply be water? It sounds like a trick. Water and electricity aren't supposed to mix. That's basic childhood safety advice. And yet, in laboratories across China, researchers have been building batteries that do exactly that. Not toy demonstrations, real, working, rechargeable batteries, published in serious scientific journals, tested for years of simulated use. So is this real? And if it is, how does a battery actually run on water? Let's start with why any of this matters. Batteries are quietly running the modern world. They're in your phone, your laptop, your car. They store the sun's energy so you can use it after dark. They keep hospitals running when the grid fails. They sit in massive warehouses, storing power for entire cities. As the world shifts toward electric vehicles and renewable energy, demand for batteries isn't just growing, it's exploding. But the batteries we depend on today, the lithium-ion cells inside almost everything, come with baggage. Their raw materials are expensive and unevenly distributed around the planet, which creates fragile, geopolitically sensitive supply chains. Their liquid electrolytes are flammable, which is why you occasionally hear about a laptop, a scooter, or an electric car catching fire. And squeezing more performance out of them is getting harder every year. So scientists have been asking an uncomfortable question. What if lithium isn't the only path forward? What if there's a completely different way to build a battery? That's where China's aqueous battery research comes in. At institutions including City University of Hong Kong, together with researchers from Southern University of Science and Technology in Shenzhen and the Songshan Lake Materials Laboratory in Dongguan, scientists have built a battery that uses a water-based electrolyte with a neutral pH, chemically gentle enough that the team compared it to tofu brine. Their results, published in the journal Nature Communications, describe a battery that survived over 120,000 charge cycles with barely any loss in performance. To put that in perspective, a typical lithium-ion battery starts noticeably degrading after 1 to 3,000 cycles. This water-based system was still going strong more than 100 times longer than that. This isn't science fiction. This is a battery that exists, that's been tested, and that's been peer-reviewed. So here's the part everyone wants explained. How can water be part of a battery? First, let's clear something up. Water isn't the fuel. It's not where the energy comes from. Think of a battery less like a fuel tank and more like a city with two neighborhoods, an anode and a cathode, connected by a highway. That highway is called the electrolyte. Its job isn't to generate power. Its job is to let charged particles, called ions, travel back and forth between the two neighborhoods as the battery charges and discharges. In a normal lithium-ion battery, that highway is built from flammable organic solvents. In an aqueous battery, the highway is built from water with dissolved salts or other compounds mixed in to help ions move efficiently. The actual electricity still comes from chemical reactions happening at the electrodes, the same fundamental principle behind every battery ever built. Water just changes what kind of road the ions are traveling on. Swap out a flammable liquid highway for a water-based one, and you get a battery that behaves very differently. And that difference is exactly why researchers are excited. Why would anyone want a water-based battery? Safety is the obvious answer. Water doesn't catch fire. That single fact eliminates one of the biggest risks associated with large battery installations: thermal runaway, the chain reaction that turns a damaged lithium-ion cell into a fireball. Beyond safety, aqueous batteries often rely on more abundant, lower-cost materials. Some designs, including recent Chinese research into iron-based flow batteries and zinc-based systems, use elements that are cheap, plentiful, and don't require the complex mining operations that lithium and cobalt do. Manufacturing can potentially be simpler too, since aqueous systems avoid some of the strict, expensive dry room requirements that lithium-ion factories need. But, and this is important, none of this means aqueous batteries are ready to replace the battery in your phone tomorrow. Because here's the uncomfortable truth. Lithium-ion became dominant for a reason. It packs an extraordinary amount of energy into a small, lightweight package. That's what lets a smartphone last all day in your pocket, or an electric car travel hundreds of miles on a single charge. Aqueous batteries have historically struggled here. The voltage window of water itself is limited. Push it too far, and the water starts splitting apart instead of storing energy. That caps how much energy these batteries can hold, compared to lithium-ion. Researchers are chipping away at this limitation with clever electrolyte designs, but it remains one of the central challenges of the entire field. So why is China throwing so much research power at a technology with real limitations? Because China isn't betting on a single battery chemistry. It's running dozens of experiments in parallel. The same country pushing lithium-ion manufacturing at massive scale is also developing sodium-ion batteries for vehicles, iron-based flow batteries for grid storage, and now aqueous systems using water as the electrolyte. It's less like a single race toward one perfect battery, and more like a portfolio of bets on very different futures. That strategy makes sense once you consider where aqueous batteries actually shine. Not necessarily in your next smartphone or electric car, at least not yet. Their real strength lies in stationary storage, massive battery installations sitting next to solar farms and wind turbines, storing energy where weight and size don't matter nearly as much as safety, cost, and longevity do. A battery that can survive well over 100,000 cycles without much degradation is exactly what a power grid wants, even if it will never fit inside a phone. So here's the catch. Before aqueous batteries change the world, they still need cheaper, larger-scale manufacturing. They need to prove they can be produced reliably outside a laboratory, and they need to keep competing against rapidly improving lithium-ion and sodium-ion technologies that aren't standing still either. This is still early-stage science, not a finished product sitting on a shelf. But maybe that's the real story here. Not that China built a battery that runs on water, but that the battery industry itself is starting to shift. It's beginning to look less like a single-minded search for one perfect chemistry, and more like a widening search for entirely different ways to store energy, each suited to a different job. So the next time someone tells you the future of energy is already decided, ask them which battery they mean, because somewhere in a lab right now, someone is testing one you haven't even heard of yet.